start. Okay, guys, once again, I welcome you to my lesson for today. So, obviously, we'll be continuing from where we left off on yesterday's lesson. So, as I was explaining, guys, I think I was explaining this part of vector. So, we're doing a little bit of revision on vector. And what we discussed was what we call a vector being a quantity which has both magnitude and direction. So we had a discussion in terms of what a magnitude means. So we said a magnitude simply refers to the size, it simply refers to the volume. So direction is just a direction which could be represented in any of those possible ways or any other similar ways normally being used in physical sciences. So most importantly, we said this 20 Newton refers to the magnitude or the size of the value of the force. So most importantly, the unit is very, very much important in physical sciences. And again, we said this is how we represent a vector quantity. And we also discussed additional vector quantities, of which you said momentum is a quantity, acceleration, velocity, etc. So what I'm thinking is I was at this part where I was trying to explain the displacement or the difference between the displacement and the distance, and again speed and velocity. So guys, I'm just going to remove all of these, and what I'm going to quickly do is to explain the difference between distance and a displacement. So let's say this is your home, and let's say this is a tree. So obviously, let's say this is a mango tree. So this is you coming out of your home, and then you travel a distance of, let's say, between your house and the mango tree, let's say is 10 kilometers. So you walk that 10 kilometers, which means in terms of the distance, guys, in terms of the distance, for you to travel from your home to the mango tree and again back home, what is the distance traveled? So let's first have a look at the distance formula. So the distance, because distance is a scalar quantity, I hope you remember that distance is a scalar quantity, and again displacement is going to be a vector quantity. So in terms of the distance formula, we only say, let's say, a distance number 1 plus distance number 2. This is going to be, to give us the total distance, plus distance number 3 plus whatever a additional distance covered. So let's see, guys, is there someone who wants to give us a guess in terms of what will the distance be to travel from home to mango tree, from mango tree back to home?
20 kilometers.
Lerato, always when you speak, your voice is always down. Guys, anyone who wants to give a guess?
Kilometers, say.
I only heard kilometers. Just make sure before you speak, your mic is completely unmuted. What is the distance?
Kilometers, say.
Let me see. Who's speaking? Who's speaking? Is it Minentle speaking?
Yes, sir.
So Minentle, what's the distance?
Can you please come again?
So I wanted to know if you travel from home to the mango tree and then from the mango tree travel back to home, what is the total distance covered?
Kilometers.
I think it's 20 kilometers.
So it's going to be 20 kilometers. I'm just not sure if Minentle was saying kilometers, but remember, kilometers is the unit for the distance. So the value of the distance is 10 kilometers. So that means you will travel 10 kilometer, another 10 kilometer, which is actually going to be 10 kilometers plus 10 kilometers, which is going to be 20 kilometers. So can you see when you calculate the distance, we are only interested in the magnitude being the value. But when we calculate a displacement, displacement, guys, it's a vector quantity. When it's a vector quantity, what does it mean? It means we take into consideration the direction. So let's say you travel in that direction, uh, and again, obviously, when you come back, you'll be traveling in that direction. So when we calculate displacement, of which we can say delta x. So the distance we can just say d, but in terms of displacement, we refer to displacement as delta x if you're traveling in this direction, either that or that direction. Otherwise, if it's up and down, then it becomes delta y, which refers to the displacement. So here comes a question, guys. Remember, in terms of the displacement, you will need to make an assumption to say either to the right as positive and then to the left as negative. So that means when you travel in that direction, your value or your magnitude is going to be positive, then in that direction is going to be negative. So the question is, if you travel from home to mango tree and then back to home, what will the displacement be?
0, sir.
0.
100%. So that means it's going to be a positive 10, a positive 10 plus negative 10, which is going to be 0. What is it? 0 kilometers. So it's more like you did not go anywhere. So, ladies and gentlemen, I'm having an understanding that you guys have a background in terms of how do we deal with vector quantity. So now let's proceed with that revision where we look at a vector. So I've already explained how to represent a vector quantity using a force. We said it's capital letter F, then we use that arrow. Remember that space over there, it's very, very much important that you fully understand that there's something which could be written there. So in short, what I'm going to quickly explain, it's something that you should have learned either in grade 10 or grade 11 in case if you're in grade 11. Otherwise, if you're in matric, it's a revision for you. So let's just do an example and say when it comes to vector quantities, they can be represented graphically. And again, we've got vectors which form an addition of vectors with subtraction. So let's have a look at addition. And then we'll also compare with subtraction. So remember, guys, everything is it's a build up towards the main course. So this is just an intro which you should not worry that much about. For some of you guys, it will be a revision, and for some of you guys, it's something new. So what I'm saying is vectors may be added or subtracted graphically. So let's have a look at when vectors are being added graphically. Let's say there's a force or whatever, but in that direction. Let me not say a force, but say there's a vector in that direction. So remember, guys, every time when you refer to a direction, let's maybe think about a campus where we've got north, east, we've got west, we've got south. Guys, I suspected a bit of disconnection. Is everything clear? Can you guys hear me when I speak? Guys, do you hear me are you able to hear me now?
Yes, sir.
Yes, sir.
Okay, so let me continue. So what I was saying is every time when we represent a vector graphically, think of a campus where you've got the origin over there. So obviously that arrow originates from the origin. So that means that a tail of the arrow it originates from the origin. So you see that arrow in the which means within an angle which is obviously less than the 90-degree angle. So for example, if you have arrow in that direction, then in your mind have that imaginary vertical and the horizontal axis where you know that arrow forms a certain angle. And again, we've got, let's say as an example, another arrow in that direction. So obviously think of this as the tail of the arrow and that being the head vectors. So obviously those two vectors can be represented as one vector. So let's see. Obviously, guys, if we try to represent that graphically on a Cartesian plane or otherwise on that vertical axis, let's say this is the y and this is the x-axis, you can start with that arrow. Obviously it originates from the origin, then it's in that direction, and again you join that second arrow from the head. So it's more like it's a head to tail representation. So you have that arrow in that direction. So to represent these two arrows by a single arrow, that's when you join from the origin to the head of the last arrow. So let's maybe take this to be arrow A and this to be arrow C. So this is going to be arrow D, which vector A. Remember, for it to be a vector to represent using that vector A plus vector C. Both of those is the same as vector D. So this is just what I wanted you guys to be aware of. I'm just not sure if it made sense to everyone, but otherwise, if you don't understand, just indicate. But it's as easy as explained. For now, don't worry that much. Again, let's now have a look at subtractions. So again, let's say you've got an arrow in that direction, which is, let's say this is vector A, and again we've got another arrow in that direction. Let's say this is vector C. So remember, guys, here we're dealing with addition, and here we're dealing with subtraction. So to represent that graphically, you start with the first vector in vector A in that direction. This is because we are looking at subtracting. You then vector C in direction, which is that's direction. Remember, above origin, we've got positive values, and below we've got negative values. So that's what influences the direction of vector C to be in the downwards direction. Let's see, this is vector C. And obviously, to represent these two vectors with a single vector, you do the same just you did on that side, where you start from the origin and then you connect to the second the vector. So that means obviously there is going to be negative subtraction, or where vectors subtract each other. So that, let's say, maybe is vector E, which means when we formulate, we are going to say a vector E is actually equals to a vector A subtracting vector C. So this is all that I wanted you guys to be aware of, or to know, in terms of the vector subtracting, adding or subtracting each other. So guys, before I move to the second part of our lesson, just indicate if everything was clear, if you were able to hear me when I speak, and again when I write over there.
Wait, I have a question.
Remember, guys, not for remember, if you have a question, don't want to from my secret. If you've got questions, go for it, because otherwise, without waiting, let's now. Let me just that I had some question. You can just go for it. I hope you'll be able to explain that, even though I've removed all of it. So just go for that question. I'll be writing something quickly before we move on.
Wait, can you explain why E is equals to A minus C?
Wait, can I explain A? What was the question? Can I explain A minus C is equals to
No,
E?
can you explain why E was equals to A minus C and we're not adding?
Okay, I think I got the question, but remember, we were dealing with two types of vectors, where in the first one we are adding, and on the second one we are subtracting. So obviously subtraction, that's where we minus. I'm not sure of how else to explain that part, but we firstly explained addition. So we ended up having vector A plus a vector C being equals to vector D. So now the second part that I was explaining, it was for subtraction. Obviously, when you subtract, it's going to be whatever vector of which it was vector A subtracting whatever vector which was vector C being equals to E. So when you represent this formula graphically, A will originate from the origin, then it's obviously in the upwards direction at a certain angle. Then from there, vector C, because you are adding. So that means from the head of a vector A, you have an option to go up or down. So in this case, because we are looking at vectors where we are adding, so it's in that direction. Then both of these can be represented by a single line, which is a line from the origin joining that part. So this is going to then be vector D. So here we are looking at subtraction. So you do the same, the first vector being A in that direction, but now because we are subtracting, so that means the second vector you have an option to go up or down, but because we are looking at subtraction, it has to go down. So these two vectors can be represented by a single vector being vector E. So this is vector E, this is vector negative C, this is vector obviously positive A, this is vector positive A, this is also vector positive C. I'm not sure if it makes sense now, but I assume it does make sense. So whoever asks the question, just make sure that you indicate if you understood. So I hope this message is going to be delivered after a few seconds. So I'll just be listening. But in the meantime, this is what I want to take you through, guys. A question says vector R makes an angle of theta with x-axis or with the x-axis. So firstly, with that statement, you know that statement is based on a Cartesian plane which has got the y-axis and the x-axis. So they are saying vector R makes an angle of angle theta with the x-axis. So obviously, ladies and gentlemen, obviously we know that that angle is going to be in the first quadrant. So you remember, guys, if it wasn't in the first quadrant based on our previous lesson on trig, it was going to be an angle. For example, if it's 180 degrees minus theta, we know it falls under that. Otherwise, if it's a plus, we know it falls in that quadrant. If it's 360 degrees minus, then we know it falls in this quadrant. But because they just said it forms an angle, then we can just assume for it to be falling within the first quadrant. So let's continue reading that statement. Remember, whoever asked the question, just make that indication in case if my explanation was a bit better. So let's see.
Yeah,
R
it made
is
sense.
broken into components, into component vectors of vector Rx and vector Ry. y. So that means in this part, I'm actually explaining what we call the components. So that means this vector r can be broken into components. So remember, from the previous example, we said a vector A plus vector C can be represented by vector D. So again, we also said, what was it? Let me just quickly check. We said vector A on subtraction, vector C can be represented by vector D. So this R, it means is the same as that D, and again this R is the same as that E. So that means two of these are what we call the components. Two of these are what we call the components. So that means we've got the X component and the Y component. What do we mean by the X component and the Y component? We simply mean we've got the horizontal component and the vertical component. So obviously the horizontal component is a component either in that direction or in that direction, depending on the quadrant in which you are. So the vertical component, it's either that vertical component or that in that downwards direction. So now let's continue to read. So they are saying vector R is broken into component vectors of Rx and Ry. So obviously, or maybe let me put it as a question to you. In which component will be that one and which component will be that one?
The one in the y-axis will be the vertical component, and the one to the right will be the vertical component. Will be the horizontal component, I meant.
So in summary, this one is going to be Rx component, and then the vertical one is going to be Ry component. Nothing complicated, guys. It's as easy as it seems. So remember, the angle formed is that angle, which is angle theta. So guys, I'm going to represent all of that information in a form of a triangle. So it's more like we've got that. Let's maybe assume that to be let's say A, and then let's assume that to be B, and let's assume that to be C. So I'm going to ask you guys a question. Which vector quantity is represented by A, which one by B, which one by C?
So C is Y and B is X, A is R.
Another one to give it a try. So remember, guys, X is the axis, Y is the axis, and in this case we are dealing with a vector components being Ry, Rx, and R. So my question is based on the vector components or component vectors and not the axis. So which vector component will be represented by A, which one by B, which one by C on this triangle?
B is Rx, C is Ry, A is R.
100%. So I hope everyone is in agreement with that statement. So it's more like this is R and this is Ry and this is Rx. Remember, these are the vectors, so we have to represent them using that. So do you guys agree that the angle formed is that angle over there? Do you guys agree with that statement?
Yes, sir.
Okay, so
Yes, sir.
that means we've got a 90-degree angle formed over there. So for the fact that we see a 90-degree angle formed over there, that means we can use the trig ratios to formulate. So obviously is those normal trig ratios that you know if you then want to formulate. So obviously cos angle theta, what will be the ratio for that? Sine angle theta, what will be the ratio for that? Tan angle theta, what will be the ratio for that?
Adjacent over hypotenuse.
Remember, guys, in terms of the vector components.
Ry over R.
For which one?
For cos theta.
So she says for cos theta is going to be Ry over R.
No, wait, it's gonna be Rx over R.
So it's going to be Rx over R, and then this one is going to be Ry over R. This one, obviously, Ry over Rx. So we are all on the same page on that one, isn't it?
Yes, sir.
Okay, 100%. So is that a question? So I suppose that was a yes. So remember, guys, this was just a bit of a revision. So now let's move on. Let's move on with our lesson for today. So, guys, at all times, ask yourself this question: what is force? So remember, guys, all that I've explained up to this point is something that you just need to be aware of. In the future, I'm going to make reference to what I've explained. So don't worry that much in case if you're not able to grab everything, but it will make a perfect sense at some point along this lesson. So guys, what is a force? Listen to this. When objects interact with each other, they exert forces on each other. Very, very much important, ladies and gentlemen. So if you've got an object there and you've got another object there, the question is, are these two objects interacting with each other?
No.
So an answer to that question, it's a no. But do you believe that they can still exert forces on each other even though they are not interacting with each other?
Yes, because they are non-contact forces.
Ladies and gentlemen, that means we've got contact forces and non-contact forces. But it's fine for now, just be aware of that. Thanks very much to Eva. So what I want you guys to understand is that when objects interact with each other, they exert forces on each other. So we can just make an assumption that because two objects exist even though they are not in contact. For now, let's just make an assumption that they do interact with each other. Let's just leave it there for now. So, guys, if a force acts on an object, it can cause a change to the object. I hope that made sense to everyone. I'm just going to repeat this for the last time. If a force acts on an object, it can cause a change to the object. That's an obvious matter, guys. So I just want us to explore some of the changes or some of the possible changes which may occur. So the first one, obviously, it could be the shape of an object. So you can just write that as part of your notes. I think the shape can also form part of the possible change. What could be the other one? Obviously, the object's state of rest. So you can just say object state of rest. The other one, guys, I think the velocity of the object could also change. So let's say the velocity of the object. And the other one, guys, most importantly, the direction in which the object moves. So that means if the force can cause change to the velocity of the object, then the moment it starts moving, it's going to move in a certain direction. So let's also add to say direction. Again, ladies and gentlemen, the acceleration, we know that as the object moves, it has the capacity to increase its velocity, which will have an influence on its direction, acceleration. So let's also add on to say acceleration. So I'm very much confident that you guys will write the correct spelling over there. So remember, guys, force, it's a vector quantity. So remember, that means a force has got both the magnitude and the direction. And I've also explained in terms of how to represent how to represent the force graphically, where we've got additions and subtractions. But most importantly, guys, I want us to now have a look at different types of forces. But before I do that, did all of this make sense to everyone in terms of what the possible changes could occur when objects experiences a certain force? Did that make sense to everyone?
Yes, sir.
Okay, so if that is the case, guys, this is what I want us to have a look at. Different types of forces. So remember, guys, all of this information that I'm explaining to you, it's going to make a perfect sense when we start with the calculations. For now, just be aware that we've got different types of forces. So I'm just not sure if I've sent all of this in the group, but if I haven't, let me just remove all of this and I'll just write each of those forces one by one. Then I'll send a picture of that. So, guys, the first type of force that I want us to talk about, or maybe let me say in physical sciences, we study these different forces. The first one being a gravitational force, or otherwise a weight, or weight. So how do we represent this? So when we talk about gravitational force, this is what we refer to as V gravity. Most importantly, remember to indicate that air. Why? Because this is a vector quantity. How do we represent weight? Is just W. I hope you remember that. So I'm just making you aware of the different types of forces that we study in physical sciences. Number 2, ladies and gentlemen, we study a normal force. Very, very much important, ladies and gentlemen. How do we represent a normal force? So you're going to say Fn. Remember, guys, let's indicate with that arrow because a force, it's a vector quantity. Otherwise, you can just say N. Very, very much important, ladies and gentlemen. The third one, frictional force. So, as I'm writing all of these, guys, these are the types of forces which you might be requested to calculate in one of the questions that we'll be doing, especially exam questions. So just be aware that as part of different types of forces that we study in physical sciences, especially in high school, it includes all of these forces that I'm mentioning in this lesson. So we represent frictional force as what? I hope you know very well that is capital letter F and that small letter F over there. The fourth one, ladies and gentlemen, very, very much important, applied forces. What? Applied forces. Applied forces, ladies
So
and gentlemen.
frictional forces, isn't it like the other way to like represent it is capital letter F and then FR?
So it's fine even if you say small letter, what is it? Small letter. Remember, this is capital letter, then this is small letter. You can still say FR. It's still fine. So it doesn't really matter that much. So either F, capital letter F, small f, or otherwise FR, it's fine. So let's leave it as FR. So again, the fourth one, applied force. So in which ways can an applied force be? Guys, if you've got, let's say, a box standing there on a horizontal surface, you can apply a force in two ways. The first way, you can push. So let's maybe say push over there. If you don't push, what do you do, guys? You pull. Very, very much important, ladies and gentlemen. So it's either you push or you pull. So guys, let's now have a look at the last type of a force that we study in physical sciences. What is it? Is there someone who wants to guess? What could be that force?
Tension.
100%. So now let's have a look at tension. How do we represent tension, ladies and gentlemen? So you can just say capital letter that and say T there. But remember, you can use that arrow to indicate. Also, you can still use capital letter D. Guys, can someone tell us why do I keep on writing that arrow at the top there? What does it mean?
It shows direction.
During
It shows
Shows that it's a
direction. The
vector.
second one, 100%. So it shows that this is a vector. What is a vector, guys?
It has both magnitude and direction.
What has both magnitude and direction?
Displacement, momentum.
So let me put it in a sense that it will make sense. Guys, what is that thing? What is that thing that has both magnitude and direction?
It's a physical quantity.
It is a vector quantity.
So it's a quantity. I just wanted the word quantity. So someone mentioned acceleration, displacement, and everything. So all of those are what we call quantities. So that means for the sake of us understanding each other, every time when I say what is that thing, then you know I'm referring to the quantity. What about that thing? What do we know about that thing? We know that that thing has both magnitude and direction. That's if it's a vector quantity. But if it's a scalar quantity, that same thing it only has a magnitude. So that means that's when we'll be talking about a scalar quantity. So ladies and gentlemen, I just want us to now have a discussion on each of those. Remember the first one I said it's what is it? Gravitational force, which is force vector G, or a acceleration that. So guys, I'm just going to be mentioning all the important stuff in relation to gravitational force. So gravitational force is the force of attraction that the earth exerts on an object above its surface. I hope you guys know very well that the earth is circular. You do know that very well, ladies and gentlemen, is it?
Yes, sir.
So everything that is circular, guys, it has got a center. A tennis has got a center. A bicycle wheel has got a center. Everything circular has got a center. Do you guys agree with that one?
Yes, sir. Yes, sir.
So according to this statement, which says gravitational force is the force of attraction that the earth exerts on an object above its surface. So this means this is the surface of the earth. So anything above, it could be somewhere there. It could be somewhere there, ladies and gentlemen. It could be somewhere there. Could be somewhere there. Could be somewhere there. Anywhere above the surface. So let's say this is you threw a stone upwards. So can you see in between that stone that you threw upwards and the surface of the earth, there is space. So does it mean the stone and the earth, are they in contact?
No.
No, sir.
So the stone and the earth are not in contact, but still, in between, guys, in between, there's a force. What do we call that force that exists between the earth and objects above the earth's surface? What do we call that type of a force?
Is it force of gravity?
Ladies and gentlemen, it's force of gravity or gravitational force. So what does gravitational force do to objects? It attracts. When it attracts, it simply means the force is in that direction. The force is in that direction. So all of these forces, guys, they are in that direction. So it's more like the earth. Is it pushing or pulling these objects?
So, sir, I'll be speaking. I have a question.
Mm-hmm.
So, like in space, it means that there's no gravity there.
So remember, LB, in this case, we are referring to yourself throwing a stone upwards. So obviously, it's going to be at a closer range and not within a range outside of, let's say, in a space. Obviously, when you throw a stone, it wouldn't get to the space, isn't it?
Yeah, that I know. I just wanted to confirm that there's no gravity in space.
Oh, yes, yes, yes. So let's say maybe what is it? The space, it's outside that broken line. So in this case, we are only considering, let's say, everything within that broken line. Anything outside is in space. So my question is this Earth exerting a pushing or a pulling force?
Pulling force.
What do we call a pulling force?
Force of attraction.
Force of attraction. So that means the Earth is attracting all of these objects towards itself. So according to the definition, the Earth is attracting all of this towards the center of the Earth. So that means this is trying to attract everything towards its center. So it doesn't matter at what point it is around the Earth's surface, but it is trying to exert everything or attract everything towards the center of itself. The other thing that I want to mention, guys, is that gravitational force acts downwards towards the center of the Earth. So that means at all times, gravitational force is acting downwards. I'm not sure if that part makes sense to everyone, but I hope it does. It's a common thing. Obviously, if you throw an object or you release it from somewhere, it will always fall downwards. So with it falling downwards, it is actually being attracted towards the center of the Earth, even though it is just going to fall and remain on the surface of the Earth. But according to the explanation, it tries to attract it towards the center of the Earth. So the other point that I want to make is that the weight, which is W, I'm now talking about W. Remember, W is the weight. So the weight of an object is the same as the gravitational force on the object. So to represent this in a form of a formula, what I'm saying is F, which is a vector quantity. So force of gravity, guys, it is equals to the weight of an object.
So we can't see the bottom part.
Sorry about that. Are you now able to see the bottom part? I hope you're now able to see everything. So what I was explaining, guys, let me just remove all of this because I think the explanation was clear there. And remember, guys, you don't need to put in this explanation in your head. Remember, this lesson is being recorded, so you just need to be careful of how you write your notes, and at the same time make sure that you listen to understand. So what I'm explaining is that the weight of an object is the same as the gravitational force on the object. So in short, it's more like we are saying, let me start with the weight because that's what I'm talking about. So it's more like I'm saying the weight of an object is the same or is equals to force of gravity. So remember both of those. So I'm not sure if it now makes sense in terms of that equation, ladies and gentlemen. I'm saying the weight of an object is the same as the gravitational force on the object. In short, it means the weight of an object is actually equals to the gravitational force. What is the formula for the weight, guys? Do you still remember the formula for the weight or FG?
Weight is equals to mg.
100% weight is equals to mg. So can you see we've got two things here? What are those things, guys? What are these things?
M represent mass, G represent
Mass.
gravitational acceleration.
So remember, guys, I just want us to also reinforce our vocabulary. So when you respond to this question, just show that you are a physics student. Say, these are two quantities. The first quantity is mass. The second quantity, what did you guys say? It's gravitational acceleration, isn't it?
Yes, sir.
100%. So remember, guys, as I say or as I talk, I try by all means to mention this physics terminology so that when we get to that stage where we deal with question papers, it's easy to understand the question. So you don't get confused by the words like magnitude, by quantities, whatever. So just make sure to mention those as we proceed with our lesson. So we've got the product of two quantities. Remember, the product, that's when you're multiplying two quantities. So in this case, we've got two quantities, but these are the product of two quantities. So what are those quantities? You guys are saying is the mass, and then this is the gravitational acceleration. Between these two, which one is a vector quantity and which one is a scalar quantity? We obviously know that mass is a scalar quantity, and then a gravitational acceleration, it's a vector quantity. What does it mean? It means mass, it has only the magnitude, and then this one, it has both the magnitude and the direction. So remember, guys, what if I've got a tennis ball, which is, let's say, 23 grams, and I've got a matchbox, which is like, let's say, a 2 gram. Remember, guys, very, very much important. In physical sciences, we measure mass in which unit, SI unit.
Grams.
The other one?
Kilograms.
So in physical sciences, we measure the mass in kilograms. Very, very much important, ladies and gentlemen. If it's given in grams, convert it to kilo. Remember, the word kilo means 1,000. So every time when we mention kilo, we talk about 1,000. So if it's given in kilo in grams, divide it by 1,000 to convert it to kilometers. Divide it by 1,000 to convert it to what is it? No, kilograms and not meters, kilograms. So that means
So wait,
we are
I have a
going to
question.
have, yes.
Wait, so do we only convert it if the question asks us to?
No. It must always be converted to kilograms. So is the SI unit for mass. So mass, it's always measured in kilograms in physical sciences, just like the velocity. If it's given in, let's say, what is it? A speed or velocity is given in 60 kilometers per hour. You need to convert it to meters per second. So look for that information that has all the physics quantities and their SI units. So SI, it represents a international symbol unit of a certain a physics quantity, which means if you go to America, if you go to wherever, guys, and you study physical sciences, we stick to the same unit being meters per second for either velocity or speed. For mass, we stick to kilograms. Ladies and gentlemen, did that all make sense to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 100%. So here comes a question, guys. My question is, since we say the weight of an object is equals to mg, do you agree that the weight is equals to mg since we say force of gravity is equals to mg? Do you guys agree?
Wait, can you please repeat?
The weight is equals to force of gravity, and force of gravity is equals to mg. Does it mean weight is equals to mg?
Yes,
Yes,
sir.
sir.
100%. So remember, the gravitational acceleration is constant and it's 9.8 meters per second squared. Do you guys remember that statement?
Yes, sir.
Yes, sir.
So that means if we've got the earth and I know CK is powerful. He can throw a fridge somewhere that high. Someone can also throw a tennis. Do you agree that a fridge has got more mass than a tennis? A tennis will have a smaller mass. Do you guys agree?
Yes, sir.
So what this formula says, it says a fridge can still have a bigger mass, bigger than a tennis. But in terms of the acceleration towards the earth, the acceleration for both is the same and is 9.8 meters per square seconds. Do you guys agree or understand that statement?
Yes, sir.
Yes, sir.
100%. So here comes a question. Between the fridge and the mass, which one has got a more force of gravity and why?
The fridge.
Why?
So since the mass of the fridge is greater than that of the tennis, I think that
100%. So that means the fridge has got more force of gravity because of the mass. So this one, it doesn't change. It's only the mass that differs from one object to another. So just be aware that when we talk about the weight, we are referring to that formula. So weight is equals to force of gravity, which is equals to the mass multiplied by 9.8. So the mass of a fridge, let's say it could be 20 kilograms. So that means when you say 20 multiplied by that, it gives a certain value, which is the magnitude of the fridge. So which is the weight of the fridge, or otherwise a gravitational force of the fridge. So obviously, if maybe we compared with a tennis which could have, let's say, 2 kg, you're going to say 2 multiplied by that, you're going to get a lesser value when you compare it with that of the fridge. That means the weight of the tennis is lesser when compared to the weight of the fridge. But there's something common about those two objects. The common thing is that they're experiencing the same gravitational acceleration. So, ladies and gentlemen, the weight of an object is the product of the mass and the gravitational acceleration of the earth. That is the explanation of this formula, ladies and gentlemen. We're saying the weight is the product of the mass of that particular object and the gravitational acceleration of the earth. So I hope that statement makes sense, guys. So I think we'll look at some more examples as we continue, but in a form of calculation. So guys, can we now move to the second type of a force?
Yes, sir.
Okay, so just make sure that you have a little bit of background in each of these forces based on what we are actually discussing. So I think on my notes, the second one, was it normal force?
yes, sir.
Yes, it was normal force.
So let's have a little bit discussion regarding a normal force. Ladies and gentlemen, very, very much important. In physics, normal simply means perpendicular to. It doesn't mean ordinary, as we know in English. We normally say. So we ordinarily say. But in physical sciences, the moment we mention normal, we are simply saying perpendicular to. Does it make sense, guys?
Yes, sir.
So,
Wait, so why do you say
ladies
it's perpendicular?
it's a term in physics that means perpendicular to.
Oh,
So
okay.
yeah, so it's not like there's maybe an explanation that I can give. So it's more like in physical sciences, when we say or we mention the word normal, we are simply referring to perpendicular to. So in this case, we are talking about a type of a force which is being called normal. So that means this is a type of a force which is perpendicular to. In terms of perpendicular to what, that's what we are going to discover. So ladies and gentlemen, as we continue to discover more of that, when an object rests on a surface, the surface exerts a force on the object called a normal force. Very, very much important, ladies and gentlemen. So we are talking about two objects here, or two things. The first one, it's a surface. A surface could be anywhere, guys. It could be a top of a table or whatever, but we're just talking about a surface. So on this surface, we've got an object which could be, let's say, a box. And maybe let's say this is a table. So ladies and gentlemen, um, uh, when an object rests on a surface, so can you see we've got a box which rests on a surface. So the surface exerts a force on the object. So that means this is the surface. It also exerts a force on the object. It doesn't necessarily mean because you've put your take a lot box on top of a table, then the box is the one which is exerting a force on the surface. Also, the surface is exerting a force on that box. So you will have a better understanding of this when we explore Newton's some of Newton's law. Some of Newton's laws. So this type of a force that is being exerted by the surface is called a normal force. So it is a contact force that acts at a right angle upwards from the surface. So, ladies and gentlemen, this is that object. So, we say this object exerts a force on the surface. In reaction, the surface is exerting a force in the opposite direction on this on that box. And very, very much important, ladies and gentlemen. So that force, it's a contact force that acts at 90-degree angle upwards. So that means if this is the box, it actually reacts at that angle of 90-degree angle. So I'm just going to quickly take you through let's say two types of diagrams where I represent both of these. But before I do that, did you grab something out of that explanation?
Yes, sir.
Okay, so remember, guys, there's what we call um, a free body diagram. A free body diagram. Remember in yesterday's lesson, I mentioned something about free body diagram and again a force diagram. Do you guys still remember me mentioning these two in yesterday's lesson?
Yes, sir.
Okay, so when an object is resting or moving on a horizontal surface, the normal force will have the same magnitude but an opposite direction to the weight of the object or gravitational force. So what it means, ladies and gentlemen, it means, let's say we've got a horizontal surface which could be a road, then we've got a car. So it doesn't matter whether this car is stationary or otherwise if this car is moving. It doesn't matter. So let me say, it doesn't matter whether the velocity is 0 meters per second or the velocity is, let's say, 60 meters per second. It doesn't matter that much. What matters the most is that the normal force will have the same magnitude but an opposite direction to the weight of the object. So that means obviously the weight of this object is in the downwards direction. Why are we saying it's in the downwards direction? Because we know the moment we talk about the weight, we are actually talking about force as a result of gravity. What is that, guys? This is the mass of the car being multiplied by g. What is g? G is the gravitational acceleration, which is constant at 9.8 meters per second. Remember, guys, as a result of g, it means this is the road which is on the surface or which is on the earth, and that road being on the earth, it means the earth, because we said is circular, it therefore has the center. So that means this is actually exiting towards the center of the earth. So now that we're talking about normal force, so normal force is actually the same thing as the weight, but in the opposite direction. That direction is actually at 90 degrees, or it's perpendicular to the weight of the object. So that means a normal force, ladies and gentlemen, I can actually say a normal force is actually equals to negative W. I'm not sure if this makes sense in a form of a formula there.
So wait, can you please explain that one more time?
Wait, which part?
The n equals to negative w, whereby that
Okay.
force opposes.
Okay, so let me remove maybe all of these because I hope it made sense to everyone. So what I'm going to do now, we've got that surface and then we've got that car. I hope all of that made sense to everyone. So we say this car has got a weight. I hope you guys agree with me on that one. So let's say this is the weight of the truck. So what is the formula for the weight, guys? The formula is mg. But remember, weight is actually force as a result of gravity. So every time when we formulate, we can start with force of gravity, which is equals to the weight, is equals to mg. Hope you all understand that part. So remember, we are talking about this type of a force, which is normal force. So it's more like normal force is the same force, but or is the same force as the gravitational force, but in the opposite direction. Why? Because we say if this is the surface and this is the object which is in contact with the surface, and the surface experiences that force as a result of that object, this surface, it is also exerting a certain force upwards, because this one is exerting downwards. So the surface is exerting the same amount of force but upwards. So that means the force of gravity of the truck, which is actually the weight of the truck, this is the same, guys, as a normal force, but in the opposite direction. So that means the negative sign, it actually refers to the direction. So the positive side refers to the direction. Remember, if it's just force, then you know it's positive force. If it's just weight, you know it's positive weight. So the positive sign, or the sign in physical sciences, it refers to the direction. Then the magnitude is the value, or the value is the magnitude, or the amount of that particular force. So remember, this is the normal force exerted by the surface. I'm not sure if you are now having an idea of what I'm trying to explain, guys.
Yes, I understand now.
Okay, so I suppose it makes sense to everyone. So now I want to explain to you the difference between a free body diagram and a force diagram. Ladies and gentlemen, just before I do that, let me start with explaining all of it. So, but so that might be it might be let's a situation where an object is resting on a horizontal surface. So let's say we're looking at an object. Let's free body diagram and again a force diagram, and notice what is the difference. So the difference is that when you do a free body diagram, you do that dot, ladies and gentlemen. And when you do a force diagram, because this is a box, then you just draw a box over there. And very, very much important, ladies and gentlemen. So remember, when you draw a free body diagram, all the arrows originates from that dot that you drew. So that means the vertical line is going to represent a certain force, and then the vertical line but in the downwards direction is going to represent a certain force, and then the horizontal the surface is also going to be represented by horizontal arrows there. So that means the horizontal line represents the surface, the vertical represents the forces. And again, because here it's a force diagram, so this is the surface, you just represent it as it is. So when we draw a force diagram, it's more like you just redraw exactly as it is, then you just show the arrows. But also notice where the arrow starts. Very, very much important, ladies and gentlemen. Notice where the arrow starts. So here comes a question. Between arrow number 1 and arrow number 2, which one is which in terms of the forces?
Arrow number 1 is the normal
Arrow number
force.
2 is force of gravity, Fg, and then arrow
100%.
number 1 is normal force.
So this is going to be Fg, and this is going to be a F normal. So you are 100% on that one, ladies and gentlemen. So sideways, we don't have any force. So the sideways arrows are not representing the force, but it's the surface. So here also, what I wanted you guys to notice is the start of the arrow. So can you see this arrow? It starts from the surface. Be very, very careful. It starts from the surface to show that it is the surface which is exerting an upward force, which is called normal force. So when it's an object, you start that arrow from the center of the object going downwards, which is going to be force of gravity. Does it make sense to everyone?
Yes,
Yes,
sir.
sir.
Therefore, it means a force. Just make sure you're able to see there. So that means force normal is equals to a force of gravity, but in the opposite direction. Does it make sense?
Yes,
Yes,
sir.
sir.
Yes, sir.
100%. Otherwise, one may say a force normal is actually equals to negative mg. But remember, we make an error there to show that gravity is a vector quantity. So, guys, if this part makes sense to everyone, I'm very much happy. Let's move on to the second part that I want to explain. Remember, this is where we were looking at an object at rest. Very, very much important, ladies and gentlemen. So, guys, when an object is resting or moving on an inclined plane or surface, the normal force will have the same magnitude but an opposite direction to the perpendicular component of the weight of the object or gravitational force. So, ladies and gentlemen, let's have a look at an object resting on an inclined plane. So, object resting on, let's say, inclined surface or plane. Very, very much important, ladies and gentlemen. So remember, these are those type of situation where we've got, let's say, maybe a box somewhere resting on an inclined. So an inclined surface, we're just referring to that surface, ladies and gentlemen. Remember, this is just a surface. So maybe it's more like it forms like a mountain. So it's more like it's a mountain over there, ladies and gentlemen. So this is that inclined surface which forms a certain angle to the horizontal. So it's more like this is a road which is a straight road, then there's a vertical bridge or a mountain or whatever, and then from there it does something like that. So we use this horizontal as reference to the angle formed as a result of that inclination. So this is going to be an angle of inclination, and that one is going to be an angle of declination. So that is the angle that they normally use in this chapter. So in this case, I want us to have a look at an object which is at rest on an inclined plane or surface. So I want us to check what happens in terms of normal force in that case. So let me just do something similar to that and say we've got a box resting over there. Very, very much important, ladies and gentlemen. So remember, guys, remember, this is that mountain, this is what it does, and whatever that happens, and we end up having that earth. So remember, an earth has got the center. So let's say this is the center of the earth. And we said, according to a force of gravity, it actually exerts from the center of that object to the center of the earth. So this is what we call a force of gravity. So a force of gravity, ladies and gentlemen, it doesn't matter whether an object is vertically like that or it's at an angle or at a certain angle. What we know is that force of gravity it exerts a force of attraction vertically downwards. Ladies and gentlemen, vertically downwards. Does that make sense, guys?
Yes, sir.
Yes, sir.
But remember now, this object is sitting on an inclined surface. So it's a surface which is not a horizontal surface, but an inclined surface, which forms a certain angle there. So what you need to be careful of is the direction in which the normal force acts. So normal force, it has got nothing to do with the earth, but the surface on which the object is resting. So the object is resting on that surface which is at an angle. And they said a normal force, it acts at right angle triangle. We said normal refers to a perpendicular to. So perpendicular to what? Perpendicular to the inclined surface. So that means a normal force, it's a force exerted by the surface. Look at where the arrow starts. So the arrow is going to start from the surface and then vertically upwards. So this is what we call a normal force. So this was a gravitational force. Does it make sense, guys?
Yes, sir.
100%. So remember, guys, this force of gravity, it's not acting in the opposite direction to the normal force. Do you agree?
Yes, sir.
And force of gravity is a vector quantity. So we can resolve this vector quantity into its components. So this is going to be the vertical component, and this is going to be the horizontal component. So the vertical component is going to be in the downwards or in that direction, because force of gravity is in the downwards direction. So also that one is going to be in that direction. So guys, this one is what we call what is it? The force of gravity perpendicular. So this is the vector quantity, or the force of gravity which is perpendicular to the surface, and that is the component of that FG. Ladies and gentlemen, this is the force, the vector force of gravity, but parallel to the surface. Does it make sense, guys?
Yes, sir.
So you remember from what we formulated, we said sorry, using what is it, using the trig ratios, the vertical component is the one with sine angle. I'm not sure if you remember, guys. And we said the horizontal component, did we say is the one with a cos? I think if we said is the one with cos angle, we will explore some of that information as we continue with our lesson. But so far, guys, did you understand that drawing in terms of how it was broken down?
Yes, sir.
No, sir, I don't understand.
No, sir, and I don't understand. In terms of FG perpendicular and FG parallel, you are saying FG perpendicular is sine theta, then FG parallel is cos theta. Isn't FG perpendicular cos theta, then FG parallel sin theta?
So there are two things. It could be that a FG perpendicular is the one which is cos theta, and it could be that is the one which is a sine theta. So that is something that we'll need to then explore as we continue with the lesson. So for now, it's not a comment that I was making. It's more like a question that I was asking, but otherwise, if there was no one to confirm, then we'll find out as we continue with the lesson. So I'm not sure if it's because you don't understand or if it's because you know for FG perpendicular to be the one, for this one to be an angle. Which one do you know? Whoever commented. One.
Sammy, I don't understand how FG is broken into components.
Okay. While we're still waiting for her to respond to that, ladies and gentlemen, here comes a question. Is this a free body diagram or a force diagram? This thing drew over here. Okay.
It's a force diagram.
Let me remove all of that. Even though I'm wondering of where I'm going to start. Let me maybe try to explain or remove and all of that. Maybe it makes sense because this part has to make sense to everyone. If it didn't, if we won't be page as we do calculations. So let me draw something similar to that and ask a question. Let me do it with Lerato. Lerato, unmute your mic. Let's have it in this. What type of a surface is this? Is it a line or is it a horizontal surface? Okay, I just remembered the message might be taking some time to deliver, but it's fine. I'll just explain. In case if you've got a question, you can ask. So, Lerato, you can now mute your mic. So, we've got two portions of the surface. Portion of AB, it's a horizontal surface. Part of BC, it's an inclined surface forming that angle theta. So that means we've got a horizontal surface and an inclined surface. So let's say we have object X which is sitting on a surface. Which surface is this? This is a horizontal surface. So because this is a horizontal surface, it means we are going to have force of gravity, which is directly downwards as force of gravity. So, and again, we are going to have normal force being force N. So in this case, because this object is sitting on a horizontal surface, there is no need to resolve any components because everything is acting vertically upwards and vertically downwards. So in this case, to formulate, we are going to say a force of gravity. It is equals to negative force of normal. So I hope this part makes sense. So let's have a look at option number 2 or scenario number 2 where we've got object Y. So on object Y, remember guys, from the center of that object straight downwards towards the towards the center of the earth, we have got force of gravity. So but can you see guys, a normal force, it won't be vertically upwards in that direction. It won't be in that direction. Why? Because a normal force, it's a force which is perpendicular to the surface. So that means the force normal is from that surface and then vertically upwards. So this is the normal force. So it starts from the surface and then vertically upwards, not necessarily vertically, but at right angle to the surface. That is where we have a normal force. So can you see, this is vertically downwards, but this is at an angle. So you cannot say force normal, you cannot equate it to Fg. Why? Because they are not acting in the same direction. This one is acting vertically downwards, and this one is acting in that direction perpendicular to the surface. And the reason why it's acting in that direction is because of the inclined or the angle formed as a result of that surface being an inclined surface. So can you see guys, which means you will have two components that you can resolve, the components of a force of gravity. Obviously this object, if it was going to move, it was going to move in that direction. And again, the force that is counteracting the normal force is that component, the vertical component of Fg. So that is the reason why we say that Fg is going to have two components. Just like what I explained initially to say on a graph, we are going to have R. So it's more like this is now R. Our R in this case is that one. So this R is going to have two components. It is going to have two components, which is R, what is it? R, maybe what we said R vertical, and again we're going to have R horizontal. I'm not sure if you guys still remember that information. So this one, this is what we refer to as a, what is it? Force of gravity parallel to the surface. It's a force that runs parallel to the surface. And then this one is going to be a force of gravity which is perpendicular to the surface. Lerato, I'm not sure if I've given a different explanation which makes you to have a better understanding. Guys, the other guys, are you now having a better understanding of what I initially explained?
Yes, we are, sir.
Yes, I understand.
So for now, just be aware that when we're dealing with an object on an inclined, we've got two components. So the components that we are having is that of the parallel and that of the horizontal. So now I want you guys to notice something. So do you now agree that force normal will be equals to negative Fg perpendicular? Remember, this is Fg. Do you guys agree?
Yes, sir. Yes, sir.
So This is the component of the force of gravity that cancels with the normal force. And this force, it's not being cancelled by anything. So that is the reason why an object on an incline is most likely to slide in that downwards direction, unless if they said maybe there was an applied force in that direction. So that is why when you formulate, you are only going to have a force applied and again force of gravity. And these two, you don't include them on the formula. Why do you not include them? Is because if the normal force is 20 Newton, we know that this one is going to be negative 20 Newton. So 20 minus 20, it's 0. So that is why we say normal force cancels out with that component. But otherwise, if it's on a horizontal surface, if that is 50 Newton, still it cancels directly with force of gravity, which is also negative 50 Newton. So on your formula you have that and that, it's already 0. But otherwise, if they said there's an applied force in that direction, on your formula you are only going to have an applied force, unless if maybe there's a frictional force. Again, also there, if there's a frictional force, if that object moves in that direction, then you're going to have applied force, a frictional force, and again that force of gravity. So you'll have 3 forces. So this one is not included in the calculations. We only consider the components of this force. And the first component, it dies because it cancels out with the normal force. So it's only this one, which is the active force, that is being added or included in the formula. So does it make sense, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so quickly, let me indicate to you that this is then going to be a force diagram. So your force diagram, remember, normal force, it's going to start from there, ladies and gentlemen, from the surface, right? And then from the center of that object vertically downwards, that's where you're going to have your force of gravity. But now, because this thing is sitting on an incline, which is an incline at a certain angle, you are forced to have those components. So this component is what we call force of gravity. Perpendicular to what? To the surface. And then this one is the component that we call force of gravity parallel to what, ladies and gentlemen? To the surface. So that means both of these components are being compared or referred or referenced to the surface. So as soon as we have done these two components, we can then say, when we calculate, we just forget about that one. So this is what we call a force diagram. So a free body diagram, we always start with that dot, then you can indicate or show that force normal in that direction. And again, you still have the same thing, guys. You have force of gravity, and then you have those components, which is force of gravity. This one is parallel. And then you also have that one, which is force of gravity but perpendicular. So this is free body diagram, this is force diagram. So that is the reason why I'm saying, in this case where you've got an object on an incline, the weight, which is equals to the force normal. This is equals to the force of gravity, but negative, which is a vector. And again, not just force of gravity, but force of gravity vertical. So that is the reason why I'm saying when I formulate, I am saying these are the two forces that cancel each other out. So it's only when an object is sitting on a horizontal surface where you say force of gravity it's equals to that, but in the opposite direction. So the formula for that is going to be force normal is equals to force of gravity. Guys, does it make sense now?
Wait, you said which two forces cancel each other?
So it's the force of gravity and the normal force when an object is sitting on a horizontal surface. And again, on an inclined surface, the force normal cancels with the force of gravity component, which is that component.
So it's the FG parallel and the perpendicular.
What is the question? Who is it? Let me see. Tand, was it Tand? What is the question? Because you're mentioning two things. So how do I answer your question? What is your question?
No, it was Elizabeth.
So I'm not sure if I answered your question, but what I was saying is a force normal cancels with force of gravity perpendicular on an inclined surface, but on a horizontal surface it's just force normal cancelling with force of gravity. So did that make sense to everyone? Does it make sense to everyone now?
Yes, it does.
Okay, so in that case, guys, I think we can end it here. I just noticed my battery is about to die, but when we continue, we will have a look at those other types of forces, because it's very, very much important that we understand all those different types of forces, so that when we get to the calculations, we fully understand what type of forces we are dealing with. So guys, in today's lesson, would you say up to what we discussed so far, does it make sense to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so in that case, guys, let's say this part brings us to the end of our lesson for today. I think I'm just not sure if tomorrow we'll be doing a maths lesson or what, but I suspect it might be a math lesson, so that for those who are not doing physical sciences, they are also accommodated. But what we have done up to this point, I think we can just leave it there, but we just need to make sure that by Sunday we finish off with this chapter, either the theory part of it, or we include the part of calculations. So just make sure that you don't miss any of these lessons. Otherwise, if you do, you can catch up. But most importantly, it's best if you attend this lesson so that you are able to ask questions to make sure that you fully understand. So guys, can we call it a day for now?
Yes, sir.
Yes, sir.
Indeed.
Okay, guys, thanks very much for joining. I hope you enjoyed this lesson as much as I did. So, guys, I will see you on our next lesson. I'll just indicate in the group if we'll be having a maths or physical sciences lesson tomorrow, but I suspect it's going to be a maths lesson where we continue with a trigonometry, especially starting with that part where we do corrections of that homework that I gave to you, and again doing some more exam type of questions. So guys, have a very good night. I'll see you in tomorrow's lesson.